Welcome back, everyone. So for today's seminar, pre-seminar, we have our very own Aaron Kettner, who will be talking about partial actions and cross products. Take it away.
Thank you. Yeah, so this week's pre-seminar is a little bit different from the usual ones, I guess, because at first it doesn't seem to have anything to do with the main talk, if you just look at the titles. But then in the proof of the main theorem, Aquila will crucially use partial actions and their cross products. And so we decided that I would introduce them now because they take some time, and then she will just be able to use them without having to spend so much time. Okay, so let G be a discrete group. And let X be, I guess, a locally compact Hausdorff space. In all the cases we care about, it's actually discrete, but in general, locally compact Hausdorff. Then a partial action of G on X consists of the following. So basically, it's a collection where we have some sets dg and some homeomorphisms theta g, where dg is an open subset of X, and theta g is a homeomorphism from dg inverse to dg. Such that I'm already out of space. So firstly, we want the domain of the identity of the group to be the entire space. And secondly, we want and we want the associated homeomorphism to be the identity. So I mean, I guess that makes sense. The identity of the group should just do nothing, and it can do nothing on the entire space. So yeah, and secondly, usually you would want that theta h composed with theta g is equal to theta gh. The problem is now this might not be, I mean, if writing inequality might not make sense due to domain issues. So we have to write, I'm going to write this. So this means that they agree on the maximal domain of this composition. Okay, so intuitively you have the space, and you have this collection of open sets, right? So that's really why it is a partial action. It doesn't take the entire space to itself, but rather it just takes some open subset to some other open subset. So let's say this is dg inverse, and then this is dg, and here you have theta g between them. And now you have like some other space, some other domain, dh inverse. This maps to dh. And now you want to compose these two, but you can't do that on this entire domain. You can only do it on those points, which then get mapped into the domain of theta g, and then you can apply it again. So somehow these partial actions, they're very similar to the usual group actions, which you're probably familiar with. But everything gets a little bit weird because you have these domains and things are not defined everywhere. Ray, you look a bit scared. Okay.
So for this thing to make sense,
Uh-huh.
right, it's H first, And that's going to go from D H inverse to D of H.
Uh-huh.
Now I lose so many, like, I know. It has to mean that the image of H is in, sorry, that D H intersection DG inverse. That's what it's defined.
Yeah, exactly. Like that should be non-empty. If that's empty, you have nowhere to go, basically. Exactly. And then that should agree, like that if this is possible to go along the action twice, then also theta GH should be defined and it should take you to the same point. Basically. Okay. Okay, so let me give you. Mm-hmm.
But the graph of the function on the left is not included in the graph. So you don't have you're not imposing any constraint on compatibility of domains. Like if I want to take the second point to mean the graph of the composition, which is maximally defined on some domain, is included in the graph of the other function, then it seems to imply that DGH must contain the graph of.
Yeah, I'm not sure.
DH minus 1, G minus 1 must contain the graph of that thing if you want to down with this. So D to the minus 1, DG, or DH to the minus 1, something like that.
I have to say, I don't usually think of it in terms of graphs, so I'm not sure if I understand that point. But I think this is, I mean, this is supposed to mean that like whenever this is defined, this is also defined, and they agree basically. Okay. Like for all points.
The DGH contains the maximum domain definition. DH minus 1, G minus 1 contains the maximum domain of the definition of the data.
Yes.
Okay,
I think so.
That's
Yeah.
right.
Okay, great. Okay, so now we see an example, which is already kind of close to the kind of example that Akila will use in her talk. So we let the space be the natural numbers, and we let the natural numbers squared, and we let the group be the integers squared. And now for any point in the group, we can define a set d minus p to be all those k in n squared, such that k plus p is still in n squared. And then we define a partial action by setting theta p to go from d minus p to dp, which I mean, like this definition is symmetric, right? You can just let the p eat the minus and then that still makes sense. Yeah, so this should just send k to k plus p. Right, so I'm defining this guy to be all those points in n squared, which I can shift by p and still land in n squared. And then you define the partial action to do exactly this. So basically, if I draw n squared as a lattice like this, it always takes a long time to draw these things. Okay, so now let's say maybe p is equal to minus 1, no, 0, minus 1. Now it's clear that if I have a point that is here, so the way I draw this, I mean, this is supposed to be 0, 0. This is 0, 1. This is 1, 1. This is 1, 0. If I take this point here, I'm not allowed to to shift this to the left, right? So this is not a globally defined action. This simply doesn't work. But what I can shift to the left by 0, -1 are exactly those points here. Right? So everything that that does not have a 0 as its first coordinate, that you can shift to the left. So the domain in this case for this point would be the 0, -1, or I guess it's the domain is minus of that. This would be all those K1, K2, where K2 is greater or equal to. Yeah. That because a point here, then, for example, I can just shift to the left. Okay. So that's an example. This is a partial action. Of z squared on n squared. And of course, this just arises as the restriction of the usual action of z squared on itself. Right, so for any group, I can act on itself by multiplication. In this case, I'm just restricting to like a semi-group sitting inside. And then you have to restrict the domains. So this becomes a partial action. Okay. So far, so good. So I hope this example makes sense. Yeah, because this is the kind of example we will see several times. Okay, what's a cross product of a partial action? And by cross product, I mean cross product C-star algebra. So we're talking about C-star algebras. Take a partial action. And I will just denote this whole thing by theta. And let's say this acts on x. So first we have to define what is a, so okay, the cross product is a C-star algebra that is universal with respect to a certain class of representations of the dynamical system. So I first have to define what's a representation of the dynamical system. So let B be a C-star algebra. A covariant representation of theta on B consists of the following. First of all, a star homomorphism from C0 of x to B. So I want to represent the C-star algebra, the commutative C-star algebra I get from the space on B. And secondly, what is called a partial representation of the group. So a map, let's say capital U from G to B. So usually you would ask this to be a group homomorphism, and maybe it goes into the unitaries on B. But in this case, we want a little bit less because we want to reflect the fact that we only have a partial action. So this should fulfill, again, U of the identity is the identity on B. Secondly, and now it gets a bit more interesting. So what you would usually ask for is that UGH is equal to UG times UH, right? So you would want this to be a group homomorphism, this map. But in this case, we will see an example of this in the end. Because everything is only partially defined, this might not quite be equal because there might be some domain issues. But this is equal if we multiply with some other guy. So if we multiply with UH inverse, then it works. And I mean, note in particular, this means that UH inverse is not just the identity. So that's a little bit weird. But think about this example, right? Here, if I have, so spoiler alert, we will be able to represent this, this partial action using shift operators on the L2 space of this guy. And if you look at a shift, for example, this shift here by 0, -1, then if I shift to the left first, and then I shift back, then I delete certain guys. Like if I shift to the left, these guys will be mapped to 0. So then if I shift back, I don't get the identity. Like somehow if you have shifts, like one-sided shifts, they are not unitaries. So that's somehow where this comes from. Maybe this gives some idea. So I don't necessarily get the identity if I compose UH and UH inverse. But there's one more, no, there's 2 more conditions, and then another one I forgot about. So you have the same thing to the left. So instead of multiplying with this thing from the right, you can multiply by UG inverse from the left. UGH is equal to UG inverse UG UH. And then lastly, this again is how you expect. So UG inverse should be UG star. And we're still not done. Now there's another condition. Now, can I just write it here? So following the such that the so-called covariance condition holds. So basically what we want is that inside B, multiplying with UG and UG star implements the action, right? So far, I have not mentioned the action at all. This is just some star homomorphism from C0 of X to B and some map from G to B. But of course, in order to have anything to do with the action, we need to impose some sort of relation, and it's exactly this. So UG pi of F, UG star should be pi of F composed with theta G inverse for all F in C0 of BG inverse. So again, you can't do this for all F, but only for those where, yeah, this composition would make sense. Yes. Okay, so that's a covariant representation. The cross product now is defined to be a C-star algebra universal with respect to these kind of representations. And so, yeah, sure.
It seems like the UG stars are kind of almost like range projections somehow, but they're not quite, they're not actually projection like this.
I mean, they can be in examples. In the example we see up there, they are.
They're just like sort of elements that you can't think of as like partial isometry.
This was exactly my question. I was going to ask the same question.
Yeah, because I mean, this looks a lot like you're kind of building a sort of graph C-star algebra out of these things where the UGs are kind of the vertices, like the ones corresponding to the edges, and then you get like
I think they're partial isometry. Like if you have like you put G equal to H inverse and that line 2 there, and you're saying UH inverse is UH inverse, UH inverse. Like say the inverse is the same thing, it's part of isometry.
Great. So they are.
Yeah.
Because what confused me is that the domains
these guys only need to be open.
Mm-hmm.
Yeah, I guess I would expect the projection to be corresponding to a closed subset.
Yeah, no, I mean, that's a good point. Whether those will be.
B, for example, would be just all bounded functions on it. Doesn't have to. Right, okay, yeah.
Mm-hmm. Yeah, no, but I mean, what Tristan said is definitely true, right? Like if you just put this thing in here, like you take H to be equal to, yeah, G inverse, and then you get the partial isomorphies. Yeah, exactly. Thank you. Yeah, I mean, I guess graphs are a good thing to have in mind if that's something yeah. Okay, nice. So now let me define the cross product. The full. So I'm not going to go into the details here. There's several cross products. The one we are considering here is called the full one because it has a universal property. The full cross product C-star algebra, written like this, is defined via the following universal property. So first of all, there exists a covariant representation on the cross product itself. So that's not technically part of the universal property, I guess, but I'm going to write it down like that. So there exists a covariant representation. Let's say pi u, where the u stands for, the small u stands for universal, of theta on the cross product itself. And for all other covariant representations, so whenever I have a covariant representation of theta on some other C-star algebra B, there is a unique star homomorphism rho from C naught of X cross G to B, such that basically, two different diagrams commute. So here I could, down here I could write C naught of X, and then I can go up using pi u, the universal covariant representation, or I can go up here and I can use pi, and then of course that should commute. And then the same thing you could do, or you probably can't see it because of this. Yes. Of course, this should commute. And similarly, the same thing should commute if we put in G. So basically, rho composed with pi u is equal to pi, and rho composed with u is equal to u. That's the thing. And of course, this doesn't, I mean, if this cross product exists, it's uniquely determined up to isomorphism by the universal property, but you have to show that it actually exists. I mean, I'm just saying, like, it should be the C-star algebra satisfying this universal property. I haven't shown that there is such a C-star algebra satisfying this universal property, but you can build it explicitly in a universal way. So this works. Okay, 5 more minutes. That's good. Okay. Anybody have questions? Otherwise, I'd go into another example. Okay, then let me just do this example. So this is a slightly more sophisticated version of the previous example, and then I will say something about the cross product as well. So we now we don't take all of z squared or n squared, but we only take like a sub lattice. So let's take all of those points where, let's say, kn plus k2 is equal to 0 modulo 2. So you'll see this is exactly the kind of example that appears in Aquila's talk. And the group should be, well, basically the same thing, but we just take our coordinates to come from z squared rather than n squared. So this is all exactly the same. The way this would look like is you have 0, 0, or if you actually compute the solutions of this guy, 0, 0, you have 1, 1, you have 2, 0, you have 0, 2, and so on. So it looks a bit like this. It's not the full lattice. You have to take out some guys. And now G is a group. This is very easy to verify. And again, just like before, we can define a partial action of G on L by setting theta to just act by addition, basically. So which is the operation of the group. And take this domain to be the maximal one possible, or k such that k plus p still lies in L. Okay. So this defines a partial action. Of G on L. And now we can explicitly represent this partial action using shift operators, as I announced earlier. So let P, SP, which is a bounded linear operator on L2 of L, be the shift. Meaning that if I take SP and I apply it to some basis vector EK, so I have an orthonormal basis of L2 of L, which is indexed by just these lattice points. So if I take EK, the basis vector, I just want to shift it to EK plus P. If that is possible, like if this guy exists, if this were, so if this, maybe I should write it differently. So this is EK plus P if K plus P is still in L and 0 otherwise. Okay, and then I can define a covariant representation by saying that pi should go from C naught of L to B of L to L. And this should just send some f in C naught of L to the corresponding multiplication operator. If I have just a C0 function on L, I can define an operator on L2 of L to just act by pointwise multiplication. So this is a multiplication operator. And you should just map any vector to the associated shift. So P gets mapped to SP. Okay, so this is a covariant representation. Now I'm running out of space. I should be done now anyways, but maybe I can take another half minute. So this is a covariant representation of theta on B of L2 of L. And so there exists a unique star homomorphism from the cross product into B of L2 of L. And it can be shown that this is injective. So this rho is injective. So it's an embedding, right? So there's a copy of this cross product inside B of L2 of L. And so that maybe gives a way to think about these partial cross products. So in this particular case, they are somehow generated by shift operators. So we can imagine like this UG over here would just be this shift operator. And that maybe also makes these weird relations a bit more understandable, like I said before, because you see that, like, for example, SP, S minus P, like the shift operator times its adjoint. This does not have to be the identity. Yeah. And with that, I think I'm done. Thank you.
Questions for Aaron?
What's the simplest example of a C-star algebra that we would know that can be realized in this way?
With a partial, from like a partial action.
So I guess for a cross product, the simplest example is the non-commutative torus.
Mm-hmm.
For this guy, something that's a partial action, but not a cross product.
Oh, yeah, it's interesting that you asked that because Karen has done a lot of research on that in the context of classification. Like, but I don't.
Hope not.
But I don't know if those are counted simple examples. So the Jiangsu algebra, for example, is a partial cross product, or AF algebras. Simple, very simple example. I think if you take, where did I put the chalk? If you take, let's say, n points, you take your space to be n points, and you take the partial action that just moves things in one direction. So then the domain would be like everything except the last point, and the codomain would be everything except the first. Then the partial cross product is just the n by n matrix algebra. That would be an example. I think so. Yeah. If you take if you just extend it to infinity in one direction, you get the tuple. If you extend it in this direction. If you have it infinite in both directions. Yes, I think then it should be like just continuous functions on this circle. So, yeah. No, the Kunz algebra. No, because for like these partial cross products usually have traces. If the group they're acting with is amenable, then like if you had a cross product, partial cross product by z squared. But I mean, I know it for sure about z. Like if you have partial cross product by z, you have. I would be surprised, but I would have to check. I'm not sure.
Any other questions? Maybe from the online audience?
Yeah, so maybe I can ask a question. Go ahead. Okay, so my question is a follow-up question to Ray's. So in algebra land, we know that an algebra is isomorphic to a cross-product algebra if and only if you have a cleaving map. Do you have something similar here that you can say that a C-star algebra is one of these partial cross products if and only if you have a certain nice map, maybe something that looks like a cleaving map, or
Algebraically, I don't know. In C-star algebra land, I'm pretty sure no. I mean, then even for the usual cross products, I think this is not. I wouldn't know of like a super simple criterion that tells you whether your C-star algebra is a cross product. I guess that's just something from algebra land, not C-star algebra land.
that's very sad, but probably true. Okay, thanks.
I have a question. So, how's this semi-direct product constructed? So, is the idea always that you take like L2 functions on this local compact host of space and shift operators induced by the partial action?
That's a great
Then,
question. So yes and no. So as I said, there's different. Now I erased it, but there's different cross products actually. Like given a partial action, you can form a star algebra, and that star algebra will always be the same. But then there exists different C-star completions. And the smallest one is called the reduced cross product, and that is constructed in exactly the way you just said. So you take like some GNS Hilbert space of C of X in this case, which would probably be some L2 space. And then you take the regular representation of the group, and then somehow you take the completion inside there. The full cross product you would have to construct in a universal way. So you would do that, I guess. By realizing it as a universal C-star algebra to say, okay, these are my generators, these are my relations, and then I just take the biggest C-star completion that exists. Yeah.
okay, that's confused me now. So the reduced one and the universal one, they still have the same universal property, but they are non-isomorphic.
No, the reduced one. So this, what I stated here, is for the full one. This is the universal property. The reduced one does not have this universal property. I should probably say that they very often agree. So if the group G is amenable, or if the action is amenable, then they will be the same. But in general, they might not be.
Okay, thank you.
Thank you.
I guess with the reduced, you need to represent the tensor products with the L2 of G as well.
Yeah, like you take like both the GNS Hilbert space and the L2 of G, and then you take the tensor.
Any other questions? If not, then let us thank Aaron again. And we'll be back in 5 minutes.